Thank you, everybody, for joining us again today. It is October 1st. We've had a real busy summer here at the JETSON AI Lab. And if you just look through the postings of all the videos that we've grown up from all these meetings, you can really see the progression of what we've done, starting with vision language models and then getting more into embodied robotics and like agentic systems as like we progressed here. Today, we're really happy to have Abrar from the Remember project that came out earlier this week. I'll share here real quick. This is a project that they released on GitHub, I think it was last week or the week before, and is one of the first deep integrations of vision language models together with ROS and these other onboard systems to do long-term memory building using VLMs and vector databases. Later in the call, we will discuss like the latest policies and multimodal LLMs that have come out and all this work that we are doing to optimize those on JETSON, basically to roll it all back together into this and the workflows that we've all been working towards with that. So with that, I'll turn it over to Abrar so he can walk us through the ins and outs of this deployment that they did. Thank you so much for coming today, Abrar.
Yeah, no, thanks for having me. Let me just get the screen share started. Switch, I have a little presentation just to quickly slide through it. Yeah, so I'm Abrar. I'm a fourth-year PhD student at the University of Southern California. And during my internship over the summer, I built this work with the help of John Welsh, Jody Biswas, Soha Pui, and Yan Cheng. The work's called Remember, Building and Reasoning Over Long Horizon Spatiotemporal Memory for Robot Navigation. So let's say that we have a robot, and this one here is from the University of Texas at Austin, where this robot just drives around the campus. And we can imagine that like when we actually deploy robots, they navigate for very long periods of time. They can be indoors or outdoors. So like here, the robot's outdoors, it's about to go inside. And they can be doing all sorts of tasks, inspection, delivery, and anything else. But these robots have seen a lot of things during its deployment, like, oh, where's the elevator? Or we might want to ask it, once it leaves this building here, you might want to ask it, oh, how long were you in this building for? And if we want to answer questions like this, traditional approaches of question answering won't really work here because we can't fit this, like, we're at like 9 minutes now. We can't fit a 9-minute video into an LLM, or we potentially could if we have like a longer context length, but eventually we're going to hit like some upper bound, right? But robots are going to be deployed for unbounded amounts of time. So that's kind of the question that we're tackling here. How do we frame this more as a memory building problem? How do we build a memory of the robot's experience over time and then use it to answer questions or generate goals for where the robot should go? So one relevant work that came out recently that I think highlights using like a long context VLM is this mobility VLA work from Google. So essentially all they do is when you're given an instruction, like you see in the top left corner, and you have like this like memory of a tour of the robot around a building, which is in this bottom left corner. They drove their robot around the Google office. They essentially just take this video and then the question and toss it into Gemini 1.5 Pro, which I think can handle about a 15-minute video. And they use that to select a navigation goal. And they have some other like topological mapping stuff that just allows the robot to navigate to that goal. But then the max video that they can handle is about 15 minutes. And that's because the 1 million context window of Gemini can't handle any longer video than that.
Okay. So they just put like literally every frame or subsample of frame into the context, like a VLM. Okay. Yes. That's interesting. Yeah. And that really currently that would only scale to cloud LLM because on like our edge VLMs, we're limited to like 8 frames max, or that's and all the optimizations we do is to keep that window as small as possible and rolling. So that is very interesting.
Yeah. So that's why. Oh, and feel free to interrupt me at any point during this presentation. Just ask questions. Yeah. So, but I think this project, Mobility Be Light, takes us in the right direction. But in our framing, we want to instead think about how do we actually accumulate these long horizon robot histories, and we do that through a memory building phase. Where we can take observations, ideally, process them somehow, and put it into like a long-term storage. And then once we have these like long histories and this like kind of memory storage, right? How do we use this memory storage to actually answer questions or generate goals about what a user may want? So here, someone might say, how do I get upstairs? And you ideally want the robot to be able to say, oh, like it should be able to query this like memory storage, and it should be able to say, oh, there's an elevator at this XYZ position, and the robot can then take you there. So that's kind of how we formulate the project, this project, and this kind of question answering is pretty common. So there's this paper called embodied question answering, or this open EQA from Meta. They're actually using this, trying to build versions of this for their Meta glasses, or like the recent ones that you might have seen on with like Mark Zuckerberg. But essentially, they have like this like video about, which is 30 seconds in length, and then they try to answer questions like, oh, what color is the kitchen backsplash, or does this house have forced air heating, or where can I store the house key? These kinds of questions take us in the right direction because they allow you to answer like open vocabulary questions, right? But for robots, this isn't particularly useful because all of these are like more generic text-based answers. And two, like the episode length here is only 30 seconds. And like I said before, robots will exist for unbounded periods of time. So this doesn't scale to that. And then similarly, Google has this work called RoboVQA, video question answering, where they try to extend this like 30-second period to about a minute or 2 minutes, where they try to ask the robot not about what the robot has done before to reason about its memory, but rather, given my 1 minute memory, what should I do next? So they're trying to tackle this like planning problem of like, what is likely to happen next, or is this task possible right now? So like overall, how we're formulating our problem, as we see in the bottom row, is we want to be on a robot. We want to be able to handle descriptive questions like that require explanations. We want to be scalably long horizon, handle dynamic scenes, be able to have some form of temporal reasoning, like asking how long were you in the building for, or be able to do positional reasoning, like, oh, what object is closer versus further away from where I want to be. And we want to be able to generate goals for the robot. So to do this, we build Remember, or Retrieval Augmented Memory for Embodied Robots. Definitely came up with the acronym first before I actually started the project. But in Remember, we have these two phases I talked about, the memory building phase and the querying phase. So in this memory building phase, in the little pink box on the left, the robot will always produce like an image of its observation, time, and a position. So we know what time it is, and we know if we assume access to some kind of like localization method, or even use just robot odometry, if you want to be a little noisy about it, we should have access to like these three pieces of information. So what we do is, as we're collecting images over time, we aggregate every 3 seconds worth of these frames into a VLA captioning model, like NVIDIA's VLA captioning model, that's able to run on device. And
Al, did you have a question there? Put your hand up.
Yeah. How often do you capture data from the frames? I would think that it's like 1 frame per second, or
so
because otherwise you're just gonna overload the thing, I would imagine.
Yeah. So for 3 seconds, VLA only handled 6 frames reliably for a video captioning, and we caption we aggregate every 3 seconds, which means in a sense we're capturing information at 2 frames per second. Yeah. So like we specifically choose to discretize here, right? With 3 seconds of frames, like a 3-second video, because we consider that like a small enough resolution or like a reasonable enough resolution for us to reason over.
I would think at this speed of these ground AMRs, like half second is acceptable. You're not going to miss most people walking by or whatnot. For high speed vehicles, we could
Actually, what I'm thinking something, is it possible like to alter the frequency according to the environment? Like, for example, if the robot is all of a sudden in an environment in which a lot of things are happening, or a truck is coming, etc., you may want to speed up the things so it does not miss any valuable data. Or if it goes to a place in which clearly nothing is going on, there's no reason to keep capturing useless, pointless data. So I don't know.
No, that's exactly it. Good. That's a really good question. So we thought a lot. We didn't try to solve this problem, I guess, but we thought a lot about the second thing that you mentioned, which is trying to like remove information, like to ignore frames where nothing interesting is happening, right? Or ignore seconds of video where nothing interesting is happening. But we kind of thought of that as like a separate problem to what we were trying to build a whole infrastructure rather than solve all of these smaller problems. And we just densely aggregate all of this information and we throw it into this vector database. And the hope is that in the second stage I'll talk about next, that the second stage actually will like reason over all of this noise essentially, of like there being not enough information or too much information. Like, because you might have like a lot of redundant information or you might have missed information. And the hope is a querying phase, like, because it's going to be, I'll talk about that later, but because it's like a quote unquote smarter LLM that can reason, like it should be able to like infer any missing information, or so we hope.
One would hope, yes. Nigel, did you have a question too?
Yeah, quick question, and feel free to just tell me to be patient if you're going to talk about it. But I'm curious, for the video captioning, did you do any sort of like structured output where you're outputting in JSON or anything, or is it just natural language caption directly into the database?
It's natural language captions directly into the database. We tried to get structured outputs from Vila, but Vila doesn't allow, like Vila doesn't, when you're asking Vila to do captioning, it wasn't trained to take in any prompts to modify the outputs of Vila. So like if you're doing regular question answer, you can ask it to do it. But for captioning, we talked with Jason Liu, the lead for the Vila team, and he said no. Like that's something they're working on, but it's not something they have yet.
Yeah. And the JETSON platform services guys, Sammy and Nigel, probably have similar experiences with Vila 3B for structured output. And so they use the larger ones in their alerts-based agent that's in shipping and JETSON platform services now. But in the future, and as maybe we'll have time to discuss later in the call, these alternative VLA, VLM architectures we're looking at will be like trained from the get-go like that. And yes, and this problem with like saliency detection essentially, and like what to process with the VLM is also a problem that they're looking at too. And they're like, oh, will you put like optical flow or background subtraction or some other saliency detector in front of it, like a trail cam essentially would do, and then just process those. Also, if you're working with like clip embeddings or SIGLIP embeddings already, which is pre-processed into this, you can very easily do like duplicate image detection with those. And it'll say, this image is already nearly identical to what's in your database, so like skip it. But okay, sorry, you can move on now.
Yeah, no, No, that makes sense. I think I'll get to more on that point.
That I believe that to be a solvable problem that you can like add on to this.
Yeah. So yeah, like for our cases, we chose to keep the memory building phase relatively simple. Like I'll talk more about this at the very end, but like there's a lot of potential things we can add on to this. So I think it's like a good solid base for a bunch of potential future work. Yeah, so now we have a bunch of captions through Vila. And so we embed it using this, it's MXBAI's Mixed Bread AI. They have a embedding model that's the best performing 300 million parameter model. We wanted to run this on JETSON ideally, so we chose something that was like reasonable in size to use. And then we take those captioned embeddings or those embedded captions along with time and position, where time is like a one-dimensional vector and position is a 2 or 3-dimensional vector, depending on your like whether you're getting 2D or 3D localization. And we use all of that and we throw it into a Milvus DB vector database. Just so our memory here is unstructured memory, or unstructured like non-parametric memory. So like, yeah, so that's how we like throw it into the vector database. And then the question is, how do we actually use this to answer questions, right? Oh, someone have a question? Right.
What's the big advantage of a vector database in comparison with a regular database or
a vector
database? Yeah.
A what database?
Yeah.
I think he's gonna like, why use a vector database for it if it's just like a simple flat array?
I don't know. I'm not big into SQL stuff, so like I don't even know what a vector database is, to be honest.
Okay, fair. Yeah. So a vector database is essentially a database that only is queryable by vectors. So these caption embeddings here are 512, or 768 dimensional embeddings, right? And now you have like a whole list of, like, if you imagine a table, we have like a whole bunch of rows of these like vectors. If we want to search through them, like given some query, right, of another vector, the best way to search for them is to do nearest neighbor search. But if you have like a super large, database, nearest neighbor is pretty inefficient. So one thing the vector database does is like, it does a bunch of like approximate nearest neighbor search techniques essentially. So it's able to like quickly search like million vector databases in like milliseconds.
For these flat indexes, if it's done right, it will just boil down to one matrix multiplication that evaluates the cosine similarity search, like with FICE or Milvus DB. At internet scale search, they employ all of these like advanced tree data structures and stuff that is like abstracted from you. But at our level, it's mostly just like a flat table of these 768 dimensional vectors and then a big matrix multiply that, and it's by virtue of using these embeddings that when you compute the cosine similarity, if they match, like it, it will be closest in space to those. And so vector DB, it doesn't necessarily mean SQL, but once you get to the higher levels of like billions or more of these embeddings in there, yes, that's necessary. And we've been working with the Milvus guys to get GPU acceleration into that and like the other accelerated DBs that we have. But for now, you can just assume like you push it in there and it will very quickly return to you the closest vector with whatever model that you're doing. If you prefer, it can literally just be like a table in PyTorch or whatnot. Yeah. So before we move on, we have one more question from Joris, it looks like here.
Hi. So my question is, you go from the video captioner to a caption and then to an embedding. Is it possible today to go from a video chunk to an embedding directly? And what are the?
Yeah, so we could do like from a video chunk straight to an embedding. That would be like the equivalent would be to go from like a clip image embedding to, or like an image to through clip to just get an image embedding. The reason we chose to do captioning first is these kinds of like more generative models tend to capture some kinds of low-level details better than just the embedding of the video itself. So that's part of our reason for, that was part of our reason for choosing to use a caption instead, because they can capture some levels of low fine-grained detail that image embeddings won't, or like video embeddings like may not necessarily capture. So that was like our reasoning for that.
Okay.
Yeah, and this was something you and I discussed throughout the summer, because we previously, I just posted a link to this NanoDB, which is like last fall we had looked at this, like how do we do super efficient image to image and like this multimodal embedded database. And what we found is with like Clip and Siglip, they are not completely balanced in like the search, like text to text search and image to image might not always return the same results. They're not completely symmetrical like that. So these learnings, you find like, well, some things work better with the text description, other things work better with just image to image. I think over time, maybe these models get more tuned for this type of real world retrieval tasks, and then we'll see more prevalence of those type of systems. But I think in the future, like going down the avenue that you suggested, George, is good to future area of expansion.
Yeah, no. Yeah.
Because ideally, we would just keep a rolling history of like every frame that comes in, you get the clip embedding or whatever for it, which is a precursor to the VLM, and just log it all, essentially.
Yeah, exactly. All right. I'm going to continue, but feel free to interrupt. Yeah, so then the second stage that we have is actually using this vector database to query given a question. So like given this vector database and given a question, like if someone is asking where's the nearest elevator, we'll have the LLM generate either a text query, position query, or time query. So what this looks like is these three things here are essentially function calls. So there's a Python function for like querying the vector database given a text input or a position input or a time input. So like for example, if given the question where's the nearest elevator, the LM would likely generate a text query for looking for an elevator, and then the word elevator is embedded, and then it queries a vector database, and we get like a bunch of potential elevators, and then that retrieved memory is added into the context of the LLM for the LLM to make another like decision, essentially. Like, so the second time around, it'll ask, should I make do I have the answer to my question, or should I make another text query or a position query or a time query? And it can repeat this process up to 3 times, or it can stop and call this answer function in which it would generate the answer, so that's currently how we have like the problem formulated. So the reason we do this like up to 3 times loop is if the LLM doesn't retrieve the right information, it can try again. Essentially, it can create a query formatted in a different way to look for this information. Or for some questions, it might require multiple steps of reasoning. Like if you remember at the beginning of the talk, I mentioned that someone might ask like, how long were you in the building for? To answer a question like that, you have to try to search for when you first entered the building and when you left the building, right? So if you have to reason about those 2 specific instances, you have to do multiple queries multiple times to try to answer questions like that. Any questions about this? I think I have a short little video to make this more intuitive, actually. So like at the first step, we see like we have like the little robot that we showed before, where it navigates for 14.5 minutes, and we create like a vector DB based on that as it moves around this campus. Then if the user asks a more generic question, like how do I get upstairs, the the LLM might generate a query like, oh, let me look for stairs because stairs is one way to get upstairs. It'll do that query and like its retrieved output. This will be in caption form, but I'm showing it as videos just to make it easy to look at. It might be some stairs that are outside, and the LLM might reason, oh, this looks like a ramp outside. That won't actually take me to the second floor. Let me try again. And then its second time, oh no. Oh no. Oh, can you guys still see this? Sorry.
Yeah, we can still see.
Yeah, we could see
Okay.
it.
Yeah. So then if the first time it failed right here, right, it didn't find the kind of question the user was asking for. The second time it might say, oh, the outdoor stairs will not take us upstairs. Let me query for elevators instead. And then it might find elevators. And then because it has a third attempt, it can try again just to get more information and search for stairs in different locations, like stairs that are inside. And then it might find some stairs that are inside actually. And then given all of this information, like it can reason about like, oh, here's all of the information that I retrieved. Let me look for the one that's closest to where my location is. And then it can generate like a navigation waypoint as shown by that star over there in terms of where to go. So this is the kind of like reasoning loop that occurs. But for each one of these queries, we actually retrieve like 3 to 5 different pieces of context. Like from the vector database, like 3 to 5 rows essentially. So like the LM has a lot more information to reason over. Yeah, so that's kind of what this step looks like. Any questions about this? After this, it's more about results.
Looks like Chris got a question here.
Yeah, so my question is, you've already said this, so I apologize for re-asking a question you've already answered. But what LLM is doing this reasoning where if it has the information, it can handle this kind of navigational question?
Yeah, so we use GPT-4o, but then we also tried a bunch of open source LLMs as well. The GPT-4o outperforms the open source LLMs by a good amount.
Okay.
So I'll talk about how we found that out. We built a small evaluation data set, but to do that, but yeah.
Okay. And the other question is, and I don't think you've mentioned this, but how much data can you store, and how does that affect performance long term?
So we can also see this. I also have results on this in the 20-minute scale, like running the robot around for 20 minutes. But I think like, let me think. Yeah, we only tested up to like 25 minutes worth of history. But I think if the robot continually saw new places and didn't like overlap into the same places over and over again, I think it could reasonably like store up to hours worth of memory. The bottleneck here is not the vector database, because the vector database, like at like an internet scale, right? People store like hundreds of millions of like vector embeddings in vector databases. But for the robot, like for a 20-minute deployment, I think we have like 400 rows, essentially 400 entries. So like it's like near instant.
You're fine. For the NanoDB, I have benchmarks that show you can do flat index up to like 5 million entries without any like, you're talking about like 10 milliseconds for the retrieval. Here it's only like way after that you would need, and then just like use Spice and they're more advanced trees. Rob,
my question definitely was related to the idea of a home assistant remembering things you talked about weeks ago or even years ago.
Yeah, so I guess theoretically could. So I think the limitation would be we only retrieve, I think the number is 5. Like for every query, we retrieve 5 entries from the vector database. But if you have a vector database with a lot of repetitive information, there's a chance that you might not, like with a very long history, right? Like a month long, right? There's a chance you might not retrieve that information in time, right? or like you might not retrieve that information from a long time ago, unless you actively like filter for like, let me retrieve something from like 5 days ago, a week ago, a month ago. But we didn't do that for this. But I do think it could work if like in this phase right here, in our memory building phase, we have these like text, position, and time queries. But in vector databases, you can also add filtering. Like you can filter for like, oh, do this like text query, but only look for information before a certain date or between these dates. We didn't choose to do that, but I'm sure if something like that was done, you could like come up with more refined queries for like the LLM to create, right?
The RAG pipelines get very advanced on enterprise side with re-rankers and all of that.
Yeah, exactly.
Yeah, it would be interesting, for example, if you left a building and then you somehow put, you know, brackets around that building as that building, and therefore you didn't search that data, that kind of thing. I'm curious how that would work.
You didn't search that? Interesting. Oh, like you can put in these like spatial, like I entered a building, I left a building as like marks essentially that you can like query from. Almost.
Yeah, basically the idea is if I'm talking about a new building I've entered, I don't need to search the last building I've already left.
Yeah, that's interesting. Yeah, I haven't thought about that. That's
I think, yeah, and I was going to look at this for like other tasks, like the robot goes and navigates somewhere and has to do something, and how does it like, how does all of that fold in once we actually start get to tasking? But I do, there are some other questions. First, we'll go to Rob and then Sebastian.
Cool. Yeah, my question was just about the images. So I know that you're using like a Villa to capture the embeddings and store those. Is there a reason why you're not maybe storing? I believe you're just storing text, right? You're not storing the image embeddings. Is that correct? Like the feature space of the images?
Yeah, we're not storing the image embeddings actually, only the caption embeddings. And the reason why is when the LM adds to the context, LMs like generally reason better over captions. So once we retrieve like some captions, like when I have this like add to context and loop section in the figure, essentially what's happening is it's taking all of those captions that it's retrieving along with the position and time, and it throws that into the context of the LLM. If we did that with images, like the amount of information we're throwing at this LLM of images just starts to become like too much almost.
The VLMs are not good at reasoning like that because they're overtuned for VQA, whereas like GPT can do that.
Got it.
Yeah.
Okay, that makes sense.
Yeah, so that was part of the reason why we chose captions the entire pipeline, partially for simplicity, but also like we could only put captions into the LLM. Yeah.
I think the ultimate elegant solution is like all modalities in all the embeddings in the database, and the VLA is able to reason over all of it in multiple steps.
Yeah, but but
we'll get there.
Yeah, we're working with what we've got now. Yeah. Cool. Any other questions?
Sebastian, do you want to go next?
Yes, thank you. Thank you very much for the presentation. Just one question from my side about, so here we are talking about the architecture on the LLM, and my point is about hardware. What kind of robot are you using here, and what kind of hardware? Is it a JETSON board, or what is it?
Yeah, we used a JETSON Orin 32 GB when deploying this on a robot. We used a Vela 3B model, and yeah,
it was running our ROS nodes that we made on the JETSON, and this all like ties together into everything we've been doing with this group. And they were one of our first users of that on actual robots. So like this whole thing's come full circle. There was one more question before we move on from Joris, and these are all great. Thanks guys for the engaging discussions.
Yes, so as I understand, your captioning and your embeddings are generated from non-overlapping video chunks. Do you see this sometimes as a problem, that you see chunks which where you don't really understand what's happening because they break up at the wrong time? And did you try to change this?
Ooh, I think the answer to that is like no. I think the only time it sometimes becomes weird is like if a person enters a frame, or like if there's a person in the frame like wearing a black shirt, let's say, and then they leave the frame and they enter the frame again, right? We're not doing any like person tracking or anything like that. So like I think sometimes when the LM reasons over like this person in a black shirt, they consider them as two separate entities rather than like the same person. I think that's the most that we see, but yeah. It doesn't, I remember it doesn't happen that much with like static objects because I think the LLM can reason about like a statue being in the same, like a statue being seen from multiple different locations are the same statue, but I don't think it does the same thing with people, I guess, just qualitatively from what I've noticed.
Yeah, and maybe it's a discount where it just doesn't get all that visual information or access to that yet, and like the balance of that, and if it's symmetrical or not. Sorry, there are a couple questions in the chat too for us to catch up with here. First one is Andy from Perry Labs. What could be the bottlenecks for productionizing this for SLAM purposes? And how does that all tie in? Maybe we'll discuss that later. But I think it is a real positive of this is like it can be integrated with existing stacks and is not completely embodied.
Yeah, no, I agree. It can be integrated with existing stacks. I think just to mention this point briefly, the integrating with SLAM specifically, the issue would be like as we throw positions into the vector database, whenever a loop closure happens, we need to be able to update the positions in the vector DB in real time. I think that's the only real change that would need to occur to make this reliably work with like an active SLAM technique. Yeah.
Gotcha. Okay. And I believe Rob can speak to this as well, because in our last meeting, he was showing how they've integrated with like VLMs and other mapping systems using like these newer transformer-based models with previous SLAM techniques as like a big sensor fusion, essentially, is what we're all going towards. And in the future, maybe that SLAM will be like NERF generated or some other like neural reconstruction of it. And it is very interesting how this is all kind of coming together from both sides of things. Okay.
The Isaac SLAM people, the Isaac mapping folks, like at NVIDIA, were interested in like. I'm not part of those conversations anymore since my internship ended, but I know they're looking into that.
Yes. Yeah. Okay. One final question before we move on. Sorry. Is it somehow possible to create an index base of images in base 60 format and do searches on that? And yes, it is possible. I put a link in there previously that would show like image to image search. It's all a matter of like what embedding model you're using. Is that sound correct, Abrar?
Yeah, that does.
Okay. All right. We can move on now. Thank you so much.
No, thanks for all the good questions. Okay, I'll just skip through the evaluation, or I'll just like breeze through this. But essentially, to evaluate our method, we build like a small evaluation data set called the Navigation Video Question Answering Data Set, or NavQA. And it's based on this like UTOS encoder data set, where there's a lot of dynamic entities and events, and it occurs at day and night, rainy, cloudy, clear days. And we have ground truth position from GPS and SLAM, and we get like images as well. So the data set contains like these like 20 to 30 minute long videos. We take 7 videos from their large data set and subsample them into like 210 questions across long, medium, and short horizons. The histogram there shows the distribution of the question lengths. But we try to ask it like 3 types of questions. Spatial, like asking like where is the closest elevator, or can you take me somewhere to get food? And the robot should be able to respond with an XYZ coordinate that tells us like this is where you should be. And then we also have temporal questions like how long were you in the building for, or like when did you see the red car on the street? Or descriptive questions like was the sidewalk busy today, yes or no? Or ask a text question, like questions with text answers, like what color were the couches in the atrium? And like, this is an offline data set, so we can evaluate and iterate on trying to build the best version of this kind of memory building and like question answering like framework essentially. So we take these long videos, build like a vector database out of them, and then we answer questions on that vector database, basically.
Yeah. This is super handy data set. So thank you, because I come on this like a few weeks ago searching for, it was like simple ground AMR data sets that have natural language instructions or questions in them, and they're basically this was one of the first ones. So that's awesome.
My understanding is NLP people would not be happy with this data set, but I think it's good for robotics people's needs.
Yeah, yes, exactly. And they are different audiences. So far, we've all survived basically by taking VQA and reusing these VLMs that are trained on YouTube videos essentially for image captioning, and are trying to like prompt engineer ourselves into reusing them for robotics. And now everybody is starting like, okay, we're getting our own data sets. We're cracking these models open. We're just gonna like go for it based on all the learnings from like the internet scale foundation models that have come out. And what we have going for us is our use cases are more narrow and we control the environments. And this is just what we need for that. So thank you so much.
Yeah, thanks. So overall, I'm just gonna talk briefly about the results, but like
Zayad from CMU has a question real quick. That's good to see you too, Zayad.
Oh yeah, good to see you too, Dustin. Question actually, I probably can wait until the end, but I might as well ask it now. And I'm not up to par on the LLM, so forgive me for that. But I wonder if there's a balance between storing the long-term memory versus short-term memory. So like me, if you ask me, where did you store scissors an hour ago? I probably remember that, but where did you store scissors a week ago or months ago? I probably don't remember that, right?
Yeah.
But if you ask me, like, where do you live? That's a long-term memory that I can retrieve. And I wonder if there's some balance that can be done there.
Yeah, I think there can be some balance with having a short-term memory phase, like in the LLM, that you can keep with you at all times. And then like you have this like long-term querying for like longer, like memories that are like further away, for example, or like memories that are more fine-grained, for example. Like you can keep coarse information in your short-term memory and then like more fine-grained memory. Like you can do some kind of like, load balancing almost with what context is in the LLM, right? Yeah. I think like,
or maybe the coarse grain maybe is the long term and the fine grain the short term.
But there is a lot of fine-grained information, right? So like you might overload the LLM with too much information almost.
Gotcha.
Yeah, so I'll talk about why I think that's a problem in like one of the next slides, in terms of like the results on this data set actually. But yeah, on this slide here actually. So the main LLM we use is GPT-4o, and we have like descriptive question accuracy to see like how well did they do on those descriptive questions, and then we have positional error and temporal error based on like the time questions or the position questions. And you'll notice that our method performs basically the best throughout. The multi-frame VLM, when we try to throw in all the information into GPT-4o as purely images, doesn't scale to like medium or long horizons. Like anything above medium is greater than 2 minutes. So like as soon as a video starts to become too long, like GPT-4o can't handle it anymore. But then the LLM with caption baseline is essentially, let's just take all the captions we've collected and throw it into an LLM, like structured based on like, hey, here's the position, here's the time, and here's a caption, answer this question for me. And it generally performs worse than our method. And one reason for this, and this is why I think that what you were asking about earlier about like storing fine-grained information only, like for the LLM to reason over, the reason why I think this one performs worse is there's almost a needle in the haystack kind of problem. Like only a subset of the information required, like only a subset of the information in your history is required to answer the question. And LLMs are generally pretty bad with like recovering fine-grained information given a super long context. So I think that's part of the reason why the LLM with caption performs slightly worse, even though technically the LLM with caption has the most information, right? Yeah, whereas ours has technically less information, but it's like more like specific. Yeah, and one thing to note, we tried a bunch of open source LLMs. We chose function calling, LLMs that are good at function calling or code generation, like Codestrel, Command R, and Llama 3.18b. We chose a smaller one on purpose. And we found that like the performance is like substantially worse, especially on like the positional and temporal error questions. And we noticed that it was because like they're bad at arithmetic. And like you would see like its reasoning process is like relatively correct, but when it has to actually like add one piece of information and another piece of information together, like for positional error, it needs to like spatially reason between two numbers, right, to see which one's closer, for example. And then they we noticed these three open source LLMs like create wildly off positions. Yeah.
And they're also not great at like the multi-step reasoning or multi-turn function calling and
exactly.
things like that. Not that it wouldn't seem impossible for them to be so, it's just that they would need tuned. And again, I think Rob, on our last meeting 2 weeks ago, we discussed like distilling, GPT-4o chain of thought to make these more robotic agents, or what is our approach as a field to developing these more agentic robotic models rather than just relying on emerging stuff in GPT and other super large cloud models for when we need it in local use. So do you have any thoughts on that, Abrar? Like if you wanted to go fine tune Llama 3B or whatnot to get that performance increased, how would you curate the data set for doing so?
That I'm not sure. Especially for like this like multi-step function calling problem.
Yeah. Okay.
Yeah.
I don't know.
But I can definitely tell you that I think like smaller models like Llama 3.18b is the right way to go. Like the other methods or even though like GPT-4 is better, it takes about like 25 seconds to go through this loop to answer questions for our method. But then for Llama 3.18b, even though it's wrong, right? But to do like 3 steps of like reasoning, right? Like up to 3 steps, it answers the question in like 8 seconds. It's like much faster.
Exactly. And even 8 seconds is way too long when you're
optimize that. Yeah.
Yes. And so I do see value in robot scientists that use, GPT-4o and whatnot to see art of the possible. But then it pretty quickly becomes an exercise in how do we optimize this for deployment, and is it distilling it down? These multi-long, like the RL reasoning that is very popular in the past month or so, it can't go off for long periods of time and do that. They've also, gotten tuned in that people are using GPT-4 to annotate the chain of thought agents and then go off and fine tune their models on that. So, and have, started cutting off people's access to that, kind of rightfully so. So if we assume that we can't distill that, what do we do then? Sebastian, question or comment perhaps?
Yes, thank you. Just one comment about the trade-off between performance and real time. Basically, we saw quite recently also Llama 3.2 with a 1B and 3B module, which are very fast. I tried that; it's very good. And in the other way, you can move to Llama 3.2. I think something like 400 billion parameters with multimodal approach. So yes, we have different trends even in our open source model, OpenWeight. I mean. So yes, what is the trend for you? The critical point is performance, real time, or accuracy?
I think we want like a reasonable amount of accuracy first, right? I think like if a user were to actually use a method like this, right? Like, okay, so people would be annoyed if it takes a long time, but I think people would be even more annoyed if they were wrong, right? If it took I think they'd be okay. Yeah. Like
it has
if
to function first. Yeah, there's not really any point if it doesn't work.
yeah. At least here, right? Like if it answers your question 31% of the time correctly, that's not that great. But then even 65 isn't that great, but I think it's a good starting point for like descriptive question answering accuracy. Yeah.
And can we consider an iterative approach where the robot can provide you a rough direction and ongoing is able to adjust and go to the right point rather than one shot?
Oh, yeah. So for those kinds of positional questions, I think like you would want some kind of like trade-off. But for like more descriptive question answering, like if someone asks you like, what did you see like a red tractor like 10 minutes ago, and it tells you like, no, I didn't when it did see one. I don't think you can correct those, but I think for the positional questions, like you can do like some amount of like you can use our method for coarse grain navigation and use another like finer grained navigation module to like do the like more fine grained navigation almost. And this is what some people in the Seattle Robotics Lab at NVIDIA are like looking at, this like more finer grained navigation step.
Interesting. Yeah. Or maybe don't ask it for exact XYZ position if it just gives you the name of the entity or whatnot. You can reverse look that up or other prompt engineering techniques for this. But I think what I'm doing on my end is kind of like absorbing all of this info about these different models, approaches, the trade-offs, and it seems like a balance between these like more chain of thought, multi-step reasoning systems versus like the embodied ones that it's just end-to-end, super easy to collect the data for that, right? Because it's just teleopt or simulated. You don't need all that intermediate state. And like, how can we like bring these all together along with the vector databases for making something that's like not too prompt engineered together and like too sensitive. So I think over time, like these Llama SLMs will be very interesting to try with the fine tunings, maybe continually so, because they are small enough to be trained on board JETSON, so we could like continue growing that over time. Okay, any more questions on this before Bob moves on? All right, thank you.
Cool. The next thing is like one thing that we noticed is if we plot on the x-axis like the length of the video, and if we aggregate these three types of questions, like the descriptive question accuracy, the positional error, and temporal error, and we threshold that into one unified like overall correctness metric, and we plot that correctness metric over time, we notice that like the LLM with captions actually like loses performance over time as it reaches like a 20-minute video. And this is because of that needle in the haystack problem that I had mentioned before. And then the multi-frame VLM, the green line, can't actually go to super long videos. So like it goes, like its performance goes down as the video becomes longer, and then it just can't answer the question anymore because its context window doesn't fit that length. Whereas ours maintains like better performance as time increases overall. Yeah. So we hope that we'd see this kind of like scaling as we reach like hours, but it's hard to get like a data set with hours worth of questions that have like good questions that are annotated, because who wants to sit around and annotate like a 4-hour long video with questions? But yeah, I think it's a good starting point.
Yeah, and it does raise like what level of natural language capability do you actually need when if you were to interact with robot on a regular basis. And like some of these models coming up have full-on like GPT level natural language. Other ones just have like single token on like the diffusion model side of those ones that do. Others are kind of in the middle, like the cross-former and whatnot. So getting a gauge on that. I know the Nebula Spot one actually does have more natural language abilities, and like you want to be able to tell like, hey, go pick up that block over there next to so-and-so. Like, okay, so you would actually converse detailed information to it. Other ones just like, hey, follow me, or just like very basic things. So perhaps that will evolve over time of like what level is actually needed for it.
Yeah. Okay, I think I'm low on time. So I'm just gonna skip these ablations.
That's okay. These meetings always go long too, so this is good.
Yeah, but overall, we deployed on this like NVIDIA Nova Carter robot. So just to show like this step, I think all the code, John, one of the authors on that paper made it all public recently for all of this part. But like first, you can build, if you build like a ROS like map of like your workspace, we can then use our like this Vila node that like Dusty and his team built that we used, along with our memory builder node that we have, and it'll build this this database given a pre-existing map. So like we assume access to a metric map beforehand. We're not doing it actively with SLAM. We can build this Milvus database, and then we can actually run the querying phase whenever we want. So we ask a question like, how do I get upstairs, like I showed before? And then a Whisper TRT speech recognition node will take in that through a microphone, publish to a speech topic. Then our agent node will take in pose information from the AMCL localization, and then query the vector database, as we see on the bottom right, until it comes up with an answer to the question. And then it can like actually take us places. So on the real robot, we only tested like the take me here, take me there kind of questions. So I'm just going to show this video. I think it's more intuitive just to watch the video, and I'll like talk through it. So we ran the robot around the NVIDIA office for like 25 minutes, just all around the place. And then we ask it questions like, we chose to ask it a question like, take me somewhere with a nice view, that's like intentionally vague, because like we were curious what its reasoning would be. And we saw something along these lines, like it thought that a pretty area will have a place with plants. This is like unprompted, like it has no like short-term memory context to reason about what's nice in its current context, but it chose plants. And then it would say, oh, plants, it retrieves areas of plants, and the office has a lot of areas of plants, and it sees like one place that it mentions is like, oh, I see a lot of plants and some in a large open space. So it starts to look for more open areas, and it sees some large windows near these open areas, near some parts of like the map that it's retrieved from. And then it looks for tall windows because it noticed tall windows exist in some parts of the building. And then it finds tall windows, and it says, oh, a large open space with plants seem to have a nice view, I'll go there. This is a summary of like the kind of reasoning that we saw when answering this question. Then it generates like a little waypoint goal, and then the robot will, then the robot will navigate there. And one thing we noticed is like it took us not all the way over there because the robot, like this method only allows for like coarse navigation almost. Like it takes us to a place where it sees where the answer to the question is. It doesn't take you exactly to where that answer to the question is, right? Because we're using the captions from images, right? It will only take us to the place where it saw the thing, not necessarily like exactly where that thing is. Yeah. And then we asked it other questions, asking it to take us to get a bag of chips, and then it takes us all the way down the office from one side to the other. And again, to like note, like we didn't tell it where the bag of chips were. The captioning model noticed that there were chips here, and it added it to the vector database. And we asked a question about like taking it to the nearest fire extinguisher. And the reason we chose this question is we know that the robot saw like dozens of fire extinguishers throughout the office space. But we were curious if we asked it to find the nearest fire extinguisher, would it actually take us to the closest one? And we let it run, and the nearest fire extinguisher is actually right next to it. We did this on purpose because we wanted to see if it actually goes to the one that we knew was next to it. And also like, because the captioning model also like is able to do some like text recognition, like this isn't like a traditional fire extinguisher, but it says fire extinguisher, and it was able to find that, which we thought was interesting.
That's actually pretty impressive. Does it know its XYZ position from SLAM map, presumably?
Yeah, we're using a localization from that map. Yeah.
Okay, cool. All right, we got a couple of questions backed up quick.
Okay, cool.
Brett was waiting, and then a couple others.
Can I let the video finish real quick and then?
Okay.
Yeah, I think there's only one more left, so I'll just talk about it. So yeah, then we asked it to take us to the water fountain, and it does. And then we ask it to take us to the elevator, and it does. Yeah. And then there we go. Okay, now I can take questions, and I can skim through the video as we need.
Regarding the selection of Whisper TRT, I'd like to just hear your thoughts on why you went with that as opposed to maybe something like Riva.
We chose Whisper TRT mostly because John, the other person helping this project, built a Whisper TRT module for like JETSON that we knew worked and he knew how to use well. So it is like the lowest effort thing we could implement in like a day or two. That is like that is basically why we chose Whisper TRT.
And we use both of those in like this group and add plugins for both. If you're on AGX currently, I would recommend Riva because it's faster and the models are bigger. John made Whisper TRT essentially for over nano, so we could fit ASR, an SLM, and TTS all on 8 gigabytes because we also got Piper for TTS. And I think just last Friday, Nemo team released new state-of-the-art ASR models called Parakeet and Canary in the 1B to 2B range that we also need to look at as well. But yeah, Riva is actually far more optimized and accurate, but is a little heavier weight or needs other containers to set up, whereas like Whisper is just easier. Did you have any follow-on questions to that, Brett?
No, that's okay. Thank you.
Yeah.
Sorry, go ahead, Deborah.
Yeah. So the reason why we chose the TRT as well, I guess, because it's smaller. Like I think we were on a 32 GB Orin, and we were basically running out of running Vila on device, Vila 3B, running the speech recognition module Whisper TRT, and like the 3D LiDAR and RAW stack took up like quite a bit of memory. So I think we were like at we were using 30 GB of the 32. So like we were cutting it close. We didn't have that much room extra. Yeah.
And there are other Whisper implementations, like faster Whisper. We had that first. And then I think Whisper TRT is another 25% faster on top of that. But it is interesting, like even with 32 gigs, you're like still running out and does speak to issue, and like Thor will have 128 or even more. So it's and we will end up using all of that too. There were a couple other hands that went up in the past few minutes. I wanted to give everybody a chance to ask questions or discuss before we move on. Anyone else? All right. Okay. If there's any more slides or anything else to show up, feel free to move on.
Yeah, it's just the last conclusion slide. So like, yeah, remember enables like good question answering and goal generation over these long robot videos. And it's like a pretty good memory representation that we can easily reason over. And like these kinds of LLM agents like we're using during the querying phase is good for reasoning over various kinds of spatial memory. But I think what's interesting is like scaling our memory building process to other kinds of external memory sources, I think is like what the next steps of something like this could look like. Like we focus on only using captions, right? And people asked about like using images as well, right? All of these could be added as extra function calls, right? Like the LM can look for an image to do an image query, or it could look for a caption by doing a text query. But also like we could use things like queryable semantic maps or scene graphs that like a whole history's worth of roboticists have worked on for like last 15 years, right? We can also incorporate interaction history or audio history, like things that are built live in real time. but we can also like use information that's given in advance. Like you have existing maps of like buildings, right? Where room numbers are, where like different offices are and stuff like that. Like that could theoretically be added as something we can query for. Or we can have users give annotations actively on a map, like this is here, that is there. And all of these things can just be different functions that the LLM can query for so that it can reason about different questions. So you might ask, if you ask the robot like, oh, take me to the coffee machine close to Dustin's office, right? Like it might be able to reason about, or it might be able to retrieve, oh, this is where the office is, this is where the coffee machine is, this is where all the coffee machines I know are, let me find the one that's like right next to it, and then let's take you there. So like these kinds of like more complex reasoning steps, I think would be really cool to see in the future.
Yeah. It would be interesting to understand these advances in graph RAG, which is like the focus of a lot of the enterprise RAG systems right now, how that could tie into all of this, given like topological nature of it. And I don't even know if you ever discussed with John, but like a couple of years ago, he had done a topological based navigation. Yeah. It was very intuitive and easy. It was pre-transformer, but it used a similar kind of approach that was like very intuitive.
Yeah. No, there's like a lot of room for cool stuff, I think.
Yeah.
Yeah.
Have you considered with like multiple robots and like having a local vector DB cache and then one like on-prem or in the cloud? Say you have multiple of these things roaming around, and how do one's memories get uploaded into the bigger system so that like if one robot saw a fire extinguisher, the other ones would then know about that.
I think that's actually like pretty reasonable to do. So we publicized our code base, and we tried to make it really easy where you can build like a memory database, like a Milbus memory, which is like the vector database, like a wrapper for the vector database along with other stuff. And you build these like memory items essentially that you can insert into the into this memory. And in practice, like our remember agent, like that does a querying phase, you set a single memory item to it. But in theory, you can set like a list of vector databases, right? And each of these vector databases are actually hosted on different IP addresses and ports. So you can theoretically have multiple, or like you can have multiple like vector databases from different robots, let's say, that you can reason over. You just have to create like a multi-agent remember agent or something, right? Yeah. So I think it's pretty reasonable to do. I think it would be cool. Yeah,
absolutely. Okay. Yeah. And I think there's so much to go on here. And in like combination with like the Rosa agent that we discussed last week, I kind of see this system in like that kind of realm where there's like higher level reasoning, perhaps multi-agent, multi-robotic coordination, long-term memory building. And then on the other side, we have going with like these embodied skills, behavioral cloning, all of that. So both in like short-term stuff and longer term, and merging that all together along with like previous work on the SLAM stacks and everything. And others in the group are similar to apply the same thing for, smart home assistants. Hal's working on like the recycling robots. And I think these approaches will, get used throughout automated systems and edge AI vision. So thank you so much for, coming today and enlightening us with all this work and everything that you've done to transition this from research into like actual deployed system that we can all see, and seems like it works great. So thank you again for presenting this all to us. At this point, we can like open the discussion for more questions or commentary, if anybody would like to. Otherwise, we have a couple more things we could cover from the past week, but just wanted to give a couple minutes for just to chat openly about this. Love your background there too, by the way, Brett. You got like a lot of systems going to manage. Alrighty. So we also had on the agenda today to get caught up with some of the other models that have come out. We've done a lot of containers in the past couple weeks, thanks to Johnny and a few others that have been working on this. I guess we'll start with, oops, sorry, I keep. The Teams thing loves to show up right where the browser is. Okay, so on Friday, Jetpack 6.1 came out, which upgrades the Jetson stack officially to CUDA 12.6, TensorRT 10.3, and cuDNN 9, which we had previously started porting our stuff to in this branch of our containers and pip server. So now we're more or less officially moving all the stuff over to that, because that's what will be production release going forward. And in the past few weeks, there's been a big buildup. In particular, all these robotics packages, the NERFs, and VLMs, VLAs. Johnny also put in this Mamba stuff. But in the past week, we got Crossformer running, Octo, diffusion policy, and 3D diffusion policy. This one is particularly interesting that does diffusion policies on 3D point clouds instead of just the RGB data. And I'd also found this Shape LLM that does similar processing on 3D point clouds with RGB and puts it through an LLM instead. So very interested to try this almost like a VLA, since that data is so easily available. And I found this when I was looking for almost like the Dino of 3D, because a lot of these robotics vision models are honing in on using Dino because the features are so rich for not only semantic but also spatial understanding. And this one is touted to be the Dino of 3D point clouds. And we're starting to see more of people just mismashing this stuff all up together with whatever encoders you want with SLMs. So I'm wanting to try these different, I think this one, the 3D diffusion policy, is using PointNet or Point Transformer, and this one is using the Recon one. So to combine that with the new Llama SLMs using this XTuner library that has really good support for training VLM models, including Lava from scratch. Some of the other ones, I had started looking at Hugging Face TRL library, which does reinforcement learners and all these other ones, but that doesn't train models completely from scratch, whereas this one does, which is necessary if say hey, I want to make a Lava with Llama 3B instead of the other one, and we're at the point now where we can just kind of go do that. Also, last week, Lava 3D paper was announced and is leading Hugging Face right now. They did not release the weights for it yet, but they would seem highly anticipated and coming soon. So it would seem everybody's kind of moving in this direction with the VLMs and the VLAs. Of course, last week, Llama 3.2 came out with the first multimodal version of that, along with the SLMs, and we have initial support for that on the Jetson AI Lab. This is unquantized because it uses a cross-attention mechanism that you actually see more in the diffusion policies and neural radiance fields being used, but it has given the quantization guys some challenges to use. Interestingly, it is way more conversational than previous VLMs, which were, super tuned for QA. essentially. So this will be interesting to play with moving forward, and we hope to continue building out this section of the site here and roll all these packages in. Like right now, we're essentially going through all of this stuff and profiling it and figuring it out. Right now, we have, these are the ones that we essentially have building: the diffusion policy, 3D diffusion policy, crossformer, Octo, OpenVLA, and some others in there. The base diffusion policy is running, and we were like training these on board JETSON even and following that. So that like is what we've been doing in the past couple of weeks is basically just getting up to speed on all the latest higher end transformer based policies and understanding and characterizing those, because there are trade-offs to each. Some of them have more natural language capabilities. Others are stronger on the vision front or can be trained very fast. In particular, the diffusion policies still seem most popular with robotics researchers coming out of the RL background. Like they've essentially stuck with like their RL sim and training environments and just upgraded their policies from being small MLPs to these diffusion models, but otherwise have kept it like mostly the same, how they're applying behavioral cloning. And it's also very interesting how they like bootstrap these with like, they'll have a small RL expert agent that they train to solve the sim task and then use that to generate data to train the actual diffusion policy and others on. And but many of these projects like Lay Robot or RUMS have not yet scaled to the larger based VLMs or VLAs, and I believe there are challenges in doing so once they get there. In particular, like wrangling all this code into mono repos, like you see with Hugging Face transformers or whatnot, that loses a lot of the fine details of the training procedures, and they have difficulty recreating the initial results. And that might be fine on some smaller ones, like the diffusion policy you can just run on your JETSON and like train that in an hour or less. OpenVLA and Crossformer ran on clusters for a couple of weeks at a time, and you're not just going to willy-nilly be able to recreate that. So our approach is to like port and build containers for each of these sub projects, profile how long the training takes and how long the inference takes. The ones that are promising we'll do optimized inference pipeline for, and still use the original repo for training, ideally on board in situ. You like drive your robot around, collect some episodes. When it's charging or like goes to sleep or you have time to wait, it'll run the training in the background and ideally build up these tasks and behaviors over time. If there's other promising models or research things you guys want to see, new VLMs coming out or whatnot, shoot them our way, and we'll take a look and get to trying those. Or if you have ones that are already working, feel free to push a PR against JETSON containers like Johnny and other community members have been doing. All of this is super valuable for all of us because there are only so many hours in the day to go off and try all of this stuff. But I believe in the long term, us all becoming like model practitioners ourselves and being able to combine the best of what's in the research for our own specialized needs, it will be, very valuable for us to do, much like people used to do with ResNets or whatnot. It wasn't such a big deal then, but these days the scale of things is more difficult. Any thoughts from the group on where we're heading with this, the direction you guys feel things are going or trends that you see in research or robotics communities that we can improve support for? Any thoughts or feedback on that? If not, we can. Yes, okay. Mizego brings up a good point about improving the circling back to the nano LLM and getting the latest SLMs in there, which we need to go back and do. A lot of times it would seem like, okay, I focus on the vision stuff really hard for a few weeks and then need to go back and get caught back up on the latest SLMs. And unfortunately for you, Mizego, the Llama SLMs coming out last week is a great impetus for us to do that. And it really seems driven on like what's the latest stuff coming out. But we will continue to profile and optimize all of these. Right now, everything seems to be coming in at around 2 to 4 FPS. Like OpenVLA, when we started, it was at 1 FPS. And when we got it fully quantized, it was at 3. And that's like the 7B level. Crossformer is at 3 FPS on AGX OREN. But that is like much harder to optimize because it's in JAX and I can't export it. Same thing for Octo. Octo is at 5 FPS, but is smaller. The 3D diffusion policy also at 3 FPS. The original diffusion policy was at like 5. So I'm trying to prioritize which one to dive into and apply optimizations to get it more in the range of like 10 FPS or real time. If you guys have any feedback on like which ones you want prioritized, that would be very helpful. In addition to looking at things on the VLM side for video analytics and like how this all ties together, because they are basically the same architectures just used for different things, and enabling everybody with these workflows to make their own special vision language model variants, I think will be essential in the longer term to actually deploy this stuff. Sebastian, you had a question quick?
Yes, basically, I know you have JETSON, Orin, and Tor, something like that, the new platform. Do you know what is the improvement on Tor?
Tor. We are, interesting question. We were just starting to like do the Gen AI bring up on that in like this week, the next couple of weeks, and we hope to have it be, in the realm of 8x, I think is what we projected when we launched it. And it'll be like a continually evolving thing, because I know they have FP4 support in Thor, the SM, I think it's like SM 101. So it's a brand new Blackwell. Thor is the first time that on Jetson, we will have the leading GPU architecture like at the time. So all previous ones we had lagged behind by a gen. So by the time it got to Jetson, it was already very well optimized in community and all the libraries and everything. This is the first time that we're going through where it's a new SM. There's no support for SM 101 in like Llama C++ or XLlama or like all of those libraries that we've previously depended on. And now we are going through all of that and will iteratively improve the performance over there. But certainly hoping for a lot higher. We do have a new secret weapon that came on board, which is Takani Chen from CMU, who makes MLC. NVIDIA, news came out over the weekend that NVIDIA had acquired Octo, which was the startup he founded for like high performance LLM inference from cloud to edge. And so now we will be able to leverage his expertise and like CMU to be able to apply all of those latest optimizations and kernels to Jetson, Thor, and these other edge devices to make sure that we are getting like ultimate efficiency out of these devices. And Jetson still is like there's no edge platform that has higher compute capability on it, which is like attracts like the latest and greatest tech and models for people that are doing stuff like this. So that's certainly our top focus, is always getting the latest transformers or diffusion models or whatever it is, which is why the JETSON AI Lab has grown in size to include all of those, from basically just starting with LLMs to now it like includes all the speech models, the robot learning policies, all the NERF stuff now. So it's really grown to like encompass everything, because everything is all coming together to support physical AI, including all the sim stuff. All right. Well, considering we're almost at 30 past the hour, it would seem a good time to wrap up. Thank you again so much.
One question, Dusty.
Sure, yeah.
Okay. Is there any tutorial to connect XRGym to the JETSON or similar thing? Because I don't have any hardware physically. So maybe the compute is on JETSON and the movement is on XRG.
What was the question to connect it to, Johnny?
Yeah, for example, use the software, for example, in a laptop, XRG, but the compute of the actions, it's like
you mean
you have the
Isaacson
environment.
Isaacson with hardware in the loop. Yes, Kabalan has done, and you've been able to do that for years with Isaacson, but he made a really nice tutorial that he presented at the AI Summit in India last weekend, and ran a workshop with that, and it seemed like it went really well. I saw him briefly here on the call earlier, but I know it's really late his time, and
because I don't have a hand or similar hardware physically, so maybe we can simulate it and
okay. He said yeah. So he plans to make like a GitHub walkthrough tutorial, or like YouTube videos on hooking up Isaac Sim with JETSON hardware in the loop, and then doing Sim to Real with his Kaya robot, and then we'll all be able to go and follow that, because like I'm going to do the same thing, get that same setup. There are previous tutorials on it, but it also changes with like, you might find one from 2 years ago with JetBot. Well, now we're on like Isaac Sim 3.0 and like Ross Humble and different versions in the connectors. So like we'll get everybody on that, and then be able to run the validation in the sim. When you get signed to life, then you can start working on real robot if you have one. Because I know Chitoku's been going through this with the lay robot and working with those coach arms, that it's very valuable just to show that like the algorithms are working in sim, the thing's learning the way that it should be. Because if you spend a lot of time on the real robot, you can spend endless debugging because something's wrong in the model or somewhere in your workflow. So even if you don't accomplish the full sim to real thing yet, which we're like scaling up all the compute in order to do that, still having that as like the validation environment is invaluable. And all of these like projects, like the 3D diffusion policy and Shapeout, they all come with their own little like custom simulator in the repo, which is like a nightmare to get these all ported and working just to test the thing. But like everybody does that and has their little sim on the side too. So yeah, that's great. If there are any other questions, I'm happy to stick around. This is like my favorite day of the week, chatting with you guys. So I really appreciate it, and all the support that you guys have given, and dedication to like what we're all doing here. Obviously, it is like gaining a lot of traction and steam, and we're getting close to it being like way more viable to deploy these systems. And essentially what we're doing is going off and seeing like what's actually usable, and transition off to the field to go and use this stuff. Our next meeting will be on October 15th in 2 weeks. We will continue profiling these models and want to get more Isaac set up on actual robot and in sim, pull in these like remember nodes. We're continuing to work with the NASA JPL guys on ROSA. So it would be interesting, Abrar, to consider how this system, we could like continue developing it with them as like the long-term memory subsystem of that in the future. Obviously, if any of your future research does tie back in or connect with that, please feel free to come on back, and would love to continue collaborating, even through you as at USC. So thanks again for everything.
Yeah, thanks. No, I do think it'd be interesting to continue it. I think based on the traction the project got, and with other people releasing similar things more recent, like yesterday, for example, I think.
Yeah, and that's great. Yeah, and I understand why it would seem like the new model for like these research projects. Everybody gets their GitHub IO page every time. It's different. There's a new repo every time. Understanding sometimes if like these projects could actually build on each other to avoid such like churn every time would be good to understand that model going forward. Sometimes with these projects, you don't really know how much effort to put into it. Like with the Open VLA, we did very extensive study on that. I have no idea if there will be an Open VLA 2 or it's just some other completely other fork of like everybody's forking instead of building on that existing project. So either just like accepting that's how it's going to be, or are there certain ones that we can rally the community behind, like LayRobot, RUMS, ROSA, or Remember, and actually like build a workflow around those that's easier to use, and kind of just like navigating how the community already works best, because that's what is the path of least resistance. All right, thank you guys so much. We can drop off now. If there's anybody else who wants to stick around and chat, please feel free to. Thanks again, Abrar, and everybody for coming out today. Great session. Thanks for all the questions, everybody. This gives us a lot of food for thought to work for next time. So appreciate it, and we'll see you again in 2 weeks. All right, take care, guys. Thanks again for coming out. See ya.